Today we're going to take a look at something called related rates. We are going to use implicit differentiation that we've already learned, but we're going to be doing it in a different way. From now on, for these related rates problems, we are going to be taking derivatives with respect to time. Related rates problems allow us to look at how different things change over time. That's why we take the derivative with respect to time, t. So every single variable that you take a derivative of, you will have d whatever over dt. So if you're taking derivative of volume, you'll have dv dt. If you're taking derivative of area, you'll have dA dt. Derivative of a radius, dr dt. Anything like that, you're going to have the d plus whatever variable it is over dt. Here is some guidelines, okay, for related rates problems. Make a list of the things that you don't know, the rates of change that you're given, constants, any formulas that are important. If they mention volume of a sphere, then you're going to have to write your volume of a sphere formulas, for example. Second, plug in any values for variables that are constant. You do not plug in a variable that is changing, but if you have a variable that is constant, you can go ahead and plug that in. Find the derivative, so differentiate your formula or equation with respect to time. So again, that's where we're using implicit. So we have to have a dt on the bottom for everything. Plug in all known values at the specific time given. And then hopefully at that point, you only have one thing left that you're solving for. If not, you've got to use the information that they give you to solve for other unknowns. And then just a quick reminder, especially if it's a free response question, make sure you're using correct units in your answer. A lot of times if it's a free response type question, they will have one point that is units. So make sure you're using correct units. Well, I think I skipped example 2 or example 1. Here we go. So here is an example that's going to look very similar to what we've done before. There's going to be one extra piece though. When we take a derivative of an x, we have to have a dx dt. When we take a derivative of a y, we have to have a dy dt. So let's take a look at this one. A particle is traveling along the curve, 6y squared, Lord, 6y squared plus x squared equals 2 plus x cubed. When the particle reaches the point 2, 1, the x-coordinate is changing at the rate of -4 inches per second. At what rate is the y-coordinate changing at this time? Okay, so I'm going to scoot this down so we have plenty of room. We are going to take this derivative. That's the first thing that we're going to need, but I will go ahead and label out some things that we know values for. We are at this time, x equals 2, y equals 1. The rate of change of x is -4 inches per second, so I'm going to call that dx, dt is -4. And it wants to know at what rate the y-coordinate is changing, so I'm going to say dy dt. There we go. All right, so now we want to take the derivative of that curve with respect to time. So let's start with our first term. We have 6y squared. So derivative of that would be 12y dy dt plus derivative of x squared is going to be 2x dx dt plus derivative of 2 is 0, so that's gone. And then derivative of x cubed is 3x squared dx dt. Now let's plug in what we know. 12 times y, so 12 times 1 times dy dt, that's what we're solving for, plus 2 times x, which is 2, dx dt, which is -4, equals 3 times x squared, so times 2 squared, times dx dt, which was -4. Now all we have is dy dt. That's the only thing we have left to solve for. So let's simplify down. 12 dy dt equals, whoops, not equals. Oh boy. 12 dy dt. And then 2 times -4 is going to be -16. Oh boy, this is hating on me today. Okay. 3 times 2 squared times -4. So we've got 3 times 4 times -4. So that's -48. If we add 16 over, Then negative 48 plus 16 is negative 32. Now we want to divide by 12. So dy dt is negative 32 over 12, which would reduce to negative 8 over 3, and our units were inches per second. Okay, we could leave it like that, or we could get a decimal if it was a calculator active problem. For one like this, you can do all of this without a calculator, so this is most likely going to be a calculator inactive type problem. All right, let's take a look at another one. A spherical balloon is being filled in such a way that the surface area is increasing at the rate of 20 meters squared per second when the radius is 2 meters. At what rate is air being pumped into the balloon at this time? Okay, so this is a lot. Let's take a look at what they gave us. Surface area is increasing at a rate of 20 meters squared per second. So that's the rate of change of your surface area. So that is, ds dt is 20 meters squared per second. And then the radius is 2 meters at this time. Okay, let's see what else. We want to know at what rate air is being pumped into the balloon. So that wants us to find dV dt, okay, the rate of change of the volume. So let's write out some things that we know. Surface area, we have the rate of change of the surface area. So let's write out what is surface area of a sphere. Surface area of a sphere is 4 pi r squared. Okay, we want to know the rate of change of the volume. So let's write out the volume equation. Volume is 4/3 pi r cubed of a sphere. Now, let's see. We want to find the rate of change of the volume. So we want dV dt. Let's take that derivative. So we want dV dt. Take derivative here with respect to time. We're going to pull that power out front. So 3 times 4/3 becomes 4, and pi is just a constant. So we have 4 pi r squared dr dt. Now, let's think about trying to plug in. We want to solve for dV dt, so that's going to stay a variable. We have the r, but we do not have the rate of change of the radius. We do not have dr dt. However, if we use surface area, we can find dr dt. So let's take derivative of surface area over here on the left. Derivative of surface area, taking derivative of 4 pi r squared gives us 8 pi r times dr dt. Now let's plug in what we know. ds dt is 20. Let's see. Then we have 8 times pi times radius, which is 2 times dr dt. So we can see that when we divide, we've got 16 pi that we are dividing by. I could get this to come down a little bit for us. I don't want to go that much. Here we go. Okay, so if I can divide by 16 pi, 20 over 16 pi is the same as what? Let's divide by 4. So 5 over 4 pi is your dr dt. So we can now plug that into our derivative of volume equation. We want to solve for dV dt. 4 pi times r we know is 2 at this time squared times dr dt we just found is 5 over 4 pi. Now, notice we have a 4 pi on the top and 4 pi on the bottom. Those cancel out. So then we have 2 squared times 5. So that ends up being 20. And then our units for the rate of change of volume would be meters cubed per second. Now, for this specific example, our rate of change dV dt and ds dt, rate of change of volume and surface area was both 20, but that will not always happen. It just worked out that way for this example. Guys, I will tell you that for sphere problems, it is very common that you have to solve for a rate of change of something to plug somewhere else. Okay, so it might have been the reverse. Maybe they gave you the rate of change of volume and they wanted the rate of change of surface area, but it's very common that you have to use both equations. All right, let's try another one. A person is standing 350 feet away from a model rocket. The rocket is fired straight up into the air at a rate of 25 feet per second. At what rate is the distance between the person and the rocket changing 20 seconds after liftoff? So in this one, if you think about starting to figure out what's going on here, this is definitely one where I would draw a picture. Okay, so you have a person standing 350 feet away from a model rocket. It's launched into the air. We're going to have a right triangle for this one. Okay, so this is definitely one that I would draw a picture for. And then I usually use A, B, and C as my sides because we know how to relate the sides of a right triangle using Pythagorean theorem. So that's just usually what I end up using. Okay, you don't have to do that, but that's usually what I do. Let's see what we know. At this time, A is 350, and that's not changing, right? The person is standing 350 feet away from the model rocket. So they're going to still be standing 350 feet away from that point, even when it's launched into the air. So I could say that I know the ADT is 0. This side is not changing. Okay, so that's a constant. Let's see what else we know. We know that the rocket is fired up into the air at a rate of 25 feet per second. So we know that the BDT is 25, the rate of change. It's positive because it's going up. And then let's see, 20 seconds after liftoff. Okay, if it's going 25 feet per second, then we could find how high it is in the air at this particular time we're talking about. We could do 25 times 20, which would give us 500. So we know that B is 500 at this point. We could do Pythagorean theorem to find side C if we need it. Let's take a look at what we need to find. At what rate is the distance between the person and the rocket changing 20 seconds after liftoff? Okay, so we want to find the rate of change between the person and the rocket. So here's the person, here's the rocket. Then C is going to be our distance between the person and the rocket. So we want to find dc dt. What is that value? So let's think about, we just talked about an equation that relates all these sides would be Pythagorean theorem. So we could say a squared plus b squared equals c squared. If we plug in something that's constant, we know a is a constant. A is always going to be 350, so we can just plug that in as a constant. Okay. The other two values are changing, okay, because the rocket is going up, and then the distance between the person and the rocket is changing. But that side A is the one that's not changing. So if we try to take derivative here, derivative of 350 squared, that's just a number, so derivative is 0. Derivative of b squared is going to be 2b db dt. Derivative of c squared is going to be 2c dc dt. And now we realize we do need that c value to be able to plug in. We already have b and db dt, but we need c. So we could quickly use Pythagorean theorem and solve for c. If we do that, we should end up with, I've already got it written out here, c is equal to the square root of 372, 500. Guys, I would just leave it as a square root. I would wait till the very end to get a decimal. The reason that I would say that is because you don't want to round too early. That will throw your answer off. Remember that your final answer needs to be accurate to 3 decimal places. So if you round early, sometimes that can totally change your answer, and you won't get full credit for the answer if it's a free response question. Okay, so just be careful about rounding too early. So let's plug in what we know now. Okay, for this one, we know that B is 25, and we know that B is 500, and dBdt is 25. C we just found to be the square root of 372,500, and we're solving for dc dt. So we want to multiply out. We would have what? 25,000 equals 2 squared, so 372,500 dc dt. Now we want to divide. Guys, be careful when you divide. Make sure you use parentheses correctly. We want to divide by the 2 and the square root of 372,500, which should give us, this is where we want to get our decimal, 20.481. And then let's think about units. We were talking about 25 feet per second for B. C is still just a side, so this is changing at the rate of 20.481 feet per second. Okay? All right. These are a pretty common type of problems, so making sure that you're good with drawing a triangle and knowing where everything fits can be very important. There's also another type with a right triangle. where you may have to look at an angle, and that's the type we're going to look at next. A person is standing 500 feet away from the launch point of a hot air balloon. The hot air balloon is starting to descend vertically at a rate of 5 feet per second. And we are, of course, pretending that we are in, perfect world where they're going to descend exactly down straight to that point and not deviate from that at all. Hot air balloon is starting to descend vertically at a rate of 15 feet per second. At what rate is the angle of elevation theta changing when the hot air balloon is 200 feet above the ground? Okay, so let's draw and label our triangle. Okay, so we've got a person standing 500 feet away from the launch point. Okay, and hot air balloon is starting to descend vertically at a rate of 15 feet per second. So if this is B, then we know dB dt is negative 15. Now, why did I write negative for this rate of change? Because it says it's descending. So you think about that actual length of B is getting smaller. So we want that to be a negative rate. Okay, the rate is implying which way it's going. So far we had increasing before on the last one. So we had a positive 25. This time we are descending at a rate of 15 feet per second. So we have a negative 15 as our rate for dB dt. All right. At what rate is the angle of elevation theta? Okay, I'm going to label theta in our triangle changing when the hot air balloon is 200 feet above the ground. So that would be our B as 200. Okay. Side C, we may end up needing that. Let's go ahead and find it with Pythagorean theorem. Okay, if we did 500 squared plus 200 squared and put the square root, our C would be 290,000, or excuse me, square root of 290,000. So again, I'm not going to change that until later. I'm not going to get a decimal till the end. Now we want to find the rate of change of the angle. So anytime you are trying to find the rate of change of an angle and you have a right triangle, you're going to end up using a trig function. So if I take a look at this, looking at this triangle, I know that A is not changing, so I can plug A in as a constant, right? B, I already have the value for that it's changing at. So I'm going to try to set up a ratio that uses the thing that I know is not changing and the rate I already have. So looking at angle theta, B and A are opposite and adjacent. So that would be a tangent ratio. I could say tangent of theta is B over, and then A we said is constant. It's always 500. We're not moving from that point. So we can plug A in as a constant, 500. Now, we want to find the rate of change of theta. So at this point, I'm going to tell you where a lot of people make a mistake, is they try to find the angle. You do not have to find the angle theta. Okay, you do not have to find that angle measure. So we're going to go ahead and just take this derivative and let's see what we end up with. If we take derivative of tangent of theta, we're going to get secant squared theta times d theta dt equals, now on the right side, remember B over 500 is the same as 1 over 500 times B, right? So that's an easy derivative to take because that's just going to be 1 over 500 times dB dt. Okay, so let's go through and start simplifying down. Now, secant squared. Okay, again, a lot of people at this point will say, well, I've got to have my angle measure so I can find what the secant of it is. But you don't. You have the triangle and you have all three sides. Think about this. Secant is hypotenuse over adjacent, right? It's the reciprocal of cosine. So secant is hypotenuse over adjacent. So that would be square root of 2,900 or 290,000, excuse me, over 500 squared times d theta dt, because that's what we're trying to solve for, equals 1 over 500 times dB dt, which is negative 15. Okay, so think about trying to simplify this down. If you wanted to get rid of what's over on the left side, we would flip and multiply. So we're going to flip and multiply by 500 over square root of 290,000 squared to get rid of that over here. So our d theta dt would end up being negative 0.26, or excuse me, negative 0.026 Now, let's talk about units. We're talking about an angle measure. So whenever you solve for one of these, it will always be in radians per time unit, which in this case was seconds. Okay, so negative 0.026 radians per second. If you left it as a fraction, that was negative 3 over 116 radians per second. Okay, and for the most part, for one like this, because your numbers are so big, this is probably a calculator active problem. So you would probably have the decimal as your final answer. Okay, but again, doesn't matter. If it's free response you're turning in for me, you could leave it either way. All right, guys, I hope this was a good start, taking a look at related rates. This is an extremely applicable concept from calculus, finding the way the relationship between different things are changing at different times. And we're going to look at a lot more examples, but hopefully this has been a good intro for you guys.